welcome back to CMOS RF integrated circuits. Today is the 19th lecture. We are going to finish what we were discussing in the previous lecture on shunt series amplifiers. That is part of module 6, wideband amplifier design, and then we are going to move on to the next module, that is noise. So, what we were discussing in the previous class, we used the method of OC time constants to figure out the different time constants. We had worked on a few of the parasitic capacitors and the load capacitor. We had not really finished our work. So, we had worked on CL over here, then we had worked on C source to body, we had worked on C drain to body, which is very similar to CL, right, and the two that remain are CGS and CGD. These two remain, and this I first want to accomplish today, and then we will move on to the next module. So, CGS, C gate to source, so this was our situation, right. I have nulled the input voltage source already, and CGS is really the capacitance across the gate to source junction, right. So, what we have to do is we have to dereference it, we have to dereference the ground to make our life easier, and then we have to do the computation, right. You agree on that? Yeah, because you know it's we are going to apply a floating voltage source and see what is the resistance. It's hard to do that, so instead we are going to dereference it, and I propose that we change our ground from what it already is So, this was my ground node. Now, I want to change it. I propose that we change it to the gate. Okay. So, I propose that we change the ground node to the gate, and then all we have to do is look into the circuit from this particular point. So, this is the business that we are about to conduct. Yes, okay. So, as soon as we try doing that, what we are going to find out is that now my circuit, I am going to redraw the circuit, looks like this. All right. This is how it is going to look like, and I need to compute the impedance looking into this particular node. Now, guess what? There is feedback going on over here. This is not going to really be in my formula. Is it going to be in my formula? No. Once again, let me just quickly double check that what I have drawn is indeed correct. No, it can't be correct. I am missing out some resistors. Okay. So, let us redraw this. So, I have got the gate connected to ground, that is fine. I need the drain to connect through 10 kilo ohms to ground. I need the drain to connect through 10 kilo ohms okay, that is better. That is better, right? Okay. So, as you see, there is some feedback going on over here, and the net result is not going to be very easy to analyze. It is not going to be easy to analyze this. Do we have something to start off from? Well, if you look at our previous computation, we had done some calculation as to finding out the resistance from some other point. This is what we had done. Okay. Now, does part of our new circuit look similar to this? Can you identify okay, not really. It should look actually similar. Maybe when I change the ground, things no longer are looking similar. That is okay, that is fine. What we are going to do is we need to analyze this. So, you pick some voltages, you write out the Kirchhoff's laws. So, I have applied a voltage V at the gate at the source of the MOSFET, and the gate is grounded. I plan to find out what is the current coming through that voltage V. Now, the good thing is that GM times V, GM, the current going through the GM, the voltage controlled current source, is very easy to find out. It is minus GMV. GM is 10 millisiemens. GM is 10 or 11. There is a body also, right, GMB. So, does not matter, I will just write 10 millisiemens times V. That is the current going through the GM cell. All right. Now, once we have that settled, let us say that this particular node is at VD. So, the current going upwards is VD by 10K, Okay. By the way, there are easier ways of analyzing this. If you study the feedback theory, this is just a form of feedback, and all you have to do is open the loop, break this particular loop over here, find out the loop gain and divide the resistance by that 1 plus the loop gain, right. That is what you have to do, which is fine. We are just going to brute force it, because I do not want to teach you the feedback theory at this point of time, and we are going to move on with our lives. Fine. What are we doing over here? Okay. We are trying to solve Kirchhoff's law at this particular node. So, I have got V d by 10 k plus V d minus V by 2 k minus 10 millisiemens times V, right, and that plus that plus this particular current. Let us say this is V x, V d minus V x by 10 k is equal to 0. This is one of the equations that I have, and the second equation is at this particular node right. So, we have got these two equations with two unknowns V d and V x, two simultaneous equations. These need to be solved, and you need to figure out what is V d, what is V x. More importantly, you need to figure out what is the current coming in from V. The current coming in from V is equal to this is what it is, right. So, keep this in the background. Remember that this is our objective. Fine. In the meantime, let us just try to solve these two equations that we have got. Let me multiply everything by 10 k to make life easier. So, I will have V d plus 5 V d, that is 6 V d, minus 5 times V minus 100 times V plus V d again and minus V x is equal to 0. That is your first equation, and the second equation gives me, let us again multiply by 10 k to make our life easy. So, 10 times V x plus again 10 times V x minus 10 times V is equal to V d minus V x. right. So, these are my two simultaneous equations. I need to solve these. So, the way you solve this is high school arithmetic, and you basically and then I add, which is going to give me 146 times Vx is 175 V. So, Vx is going to be about 175 divided by 146. This is something that I am not used to doing orally, but anyway it is something like 7 by 6. So, 1.17. Yeah. Let me just write 1.2. Okay. And the next one, Vd, I can get from Vx. So, 7 times Vd minus 1.2 V. So, Vd is about 15 times V. Right, and then I plug in all these numbers over here. So, V minus Vx is about minus 0.2, V minus Vd is minus 14, which means that the resistance looking in over there is about 1 by 2.8 millisiemens. So, that is about maybe something like 300 ohms. Little more, 350 ohms. So, all these calculations you have got to do carefully. Now, CGS is 200 femtofarads, I have got 350 ohms over there. So, I should be getting something like 350 times 200, so about 70 picoseconds. All right. And lastly, I am left with CGD, C gate to drain. Now, gate to drain is also going to be similar. And for this you are going to apply your voltage over there across the gate and drain. Now, one nice thing about this is that the 10K is going to come in shunt with everything else, right. So, what we are going to do is, once again we are going to dereference the voltage, the ground. We are now going to call the gate as my new ground. Okay. And when I call the gate the new ground, I am going to redraw this circuit. as this. Once again there is the element of feedback which is going to create some problems for me, but I do not fear these problems. I just redraw the circuit in this fashion. I apply my voltage and I want to find out what is the current coming in. Have I redrawn the circuit correctly? It looks like I have done it correctly. All right. So, this is the plan. Now, replace the MOSFET with its model. Okay. So, the first thing is that the 10K comes in shunt with everything else. So, let us remove that particular story altogether. The next thing, what is the impedance that I see when I look in upwards from this particular point? Let us make life a little easier. What is that impedance that I see? This is easy to find out, right? Is it easy to find out? What is the impedance that you see when you look in upwards from that point? We have done it before, just now. Agreed? We have done it before just now, the same story. So, looking in upwards from here we see about 350 ohms. Looking in downwards from here we see about 1K. So, what do you expect? Looking in from here, I am sorry, you see 1.35K over here. So, looking in here we saw 350 ohms, looking into the source we saw 350 ohms. So, looking into this point over here we see 1K plus 350 ohms. Okay. So, looking into this junction I see on one side 1K, on the other side 1.35K. Right. Therefore, I now have got a network. I have applied some V 10K and it splits into two pieces, 1K and 1.35K. I need to find the voltage over here. It is easy to find, right. 1K parallel 1.35K is about 0.6K. So, I have applied V, it is a resistive divider, 10K and 0.6K should give me something like how much? V by 14 or something like that. No. Yeah, V by 14 or so. V times 0.07 or so. All right. So, once I know this, my life should be a little bit easier. I have the next thing is what is the current that is going upwards over here. I have 0.07 times V. The impedance that I see looking into that particular node is 1.35 K. So, the current going upwards is going to be 0.07 volts divided by 1.35 K. Right? What is the current this way? Current this way is V minus 0.07 V divided by 10 K. So, that is about 0.0. Right. So, the net current coming in over here is something like this. That is the net current coming in over there, and then I need to quickly do the mathematics, the calculation, and find out how much is the current exactly, and that is going to give me the resistance. Okay. This mathematics, this calculation is beyond my mental arithmetic capabilities. So, I am going to pause over here, and I am just going to assume that you have found out the correct number. Right. So, that is basically going to give you something for CGD over here. I have not computed this because it is too difficult for me to do it orally. You will have to do it, and you will have to work out exactly how much is the time constant that you see. Now, do you think it is going to be large, small, in kilo ohms or in ohms, hundreds of ohms? What do you think is it going to be? So, 0.93 by 10 K is something like this. And the other one is probably going to be something like this. So, you are basically going to see a large resistance over there. That is what you anticipate. $30 kilo ohms or so, right. Now, 30 kilo ohms in shunt with, you have already got a 10 kilo ohms over there. 30 kilo ohms in shunt with 10 kilo ohms is about how much? $23 kilo ohms or so. So, what we are going to see over here is (50 femtofarads with 23 kilo ohms is going to give me a substantial number. femto. So, 100 femto times about 12 kilo ohms, 11 kilo ohms. 100 femto times 11 kilo ohms is 100 pico times 11. So, it is about 1100 picoseconds. Okay. So, this is still going to be a problem for us. Now, in addition to this, do you think there is also going to be a 0 over here? Yes, there is going to be a 0. We unfortunately have not been able to estimate the location of the 0 with our method of open circuit time constants. So, the 0 is going to enhance the bandwidth. All of these other time constants, these are all small. CdB is also not really very large. What's going to affect you are the load capacitance and CGD. Now, you can fix both of these. CGD is usually fixed by using a cascode structure, remember. So, you can put a cascode over here, same topology, and try to fix the CGD. Load can be fixed with a buffer. So, you can work on these things and make a real good wideband amplifier. All right. These are basically methods of making wideband amplifiers. What we have, let me try to summarize. What we have seen so far is that you can trade off a few things to get more bandwidth. Number one, you have all heard of the gain bandwidth product. So, you can trade off gain to get more bandwidth, right. However, the gain bandwidth product is really when you have got an all pole transfer function and then you apply feedback and so on and so forth. Gain bandwidth product, gain goes down, bandwidth goes up. Okay. This is really when I have got all poles, when I have got feedback around the system, etc. The other strategy that we have got is by inserting zeros, strategically inserting zeros by using complex conjugate pole pairs. By increasing the order of the network. All of these cost me in terms of delay. Delay is something which I can tolerate. If I reduce the gain, my system becomes less useful. If I increase the delay, there is no harm. So, I can increase the delay and I can get bandwidth in lieu of some more latency in my circuit. So, this technique is used a lot of times. All of the earlier techniques by placing an inductor, T coil, etc., were basically to emphasize this fact that you allow the response to be delayed, but it is going to be sharper. So, instead of getting a slow response starting now, I will get a fast sharp response starting a little later. This is basically the idea. There are ultra wideband amplifiers which use a cascaded stage of a lot of transistors, lot of stages, and these particular techniques, they are used a lot of times in microwave circuits, etc. These particular techniques also play with the delay. So, you basically say that let me get my signal later, but I want a sharp signal with large bandwidth. So, these are general techniques that are used. The other technique that we did not discuss is under principles of wideband circuits, is when you cascade amplifiers, you can try to follow the Butterworth transfer function instead of just cascading and getting the same pole location every time. So, this we did not discuss, I am not going to go into that. So, this could be your extra reading. So, it is like this. Suppose I want a gain of 1000. I can get a gain of 1000 by cascading 3 amplifiers, each of gain 10, right. Each amplifier is going to give me its own pole, its own delay. Now, what you have to do is something like this. So, suppose you want a gain of 1000, let us say you have got some op amps with you. I mean, the op amp is just to make life easy. Okay, you can replace the op amp with your own transistor circuit over here. It is just illustrative. So, this is one way of getting a gain of 1000, right. You put 3 successive amplifiers, each of gain 10. Now, this is one way of doing it. The other way could involve something a little more complicated. So, what this is going to give is as follows. This is going to give one pole at a certain location. This is going to give a pole at the same location. This is going to give a third pole at the same location. So, your net transfer function H of S will basically be 1000 divided by 1 plus S by omega p whole cubed. All right. So, instead of this, can you arrange these 3 amplifying stages in a way that you get your pole locations differently? Can you arrange your 3 amplifying stages in a way that you get this kind of a transfer function? So, this is the Butterworth transfer function. It can be done. So, you say that I no longer want to put a simple cascade of 3 amplifiers like that. I would like something more complicated. Why not something like this? Okay. This also could be made, something looking like that looks like this could also be designed, and this also could be designed to have a gain of 1000, and this will probably have more bandwidth than what you have got over there. Now, you will not have the same location of the poles anymore, right. So, one can do all these things to get more bandwidth. Now, you replace your this op amp that I have drawn over here with your favorite circuit, amplifying circuit, etc. So, basically a wide banding technique is when you cascade amplifiers, instead of having repeated poles at the same place, try to find out a strategy where you can have a Butterworth polynomial at the in the denominator. That will give you maximally flat bandwidth, the largest possible bandwidth in fact. All right. So, on this note I am going to end this discussion, and we are now going to move on to the next topic, next module, that is noise. Okay. And the module after this we are going to start discussing the real stuff, that is the low noise amplifiers. So, this is the prelude to that. Noise. Now, first of all, what is noise? Noise is a random process which is because when you have a resistor, and when you have, let us say you have got current moving through a resistor, it is really a lot of electrons in this material that are moving through, and the electrons are jostling with each other, hustling and bustling and pushing each other, and they are all actually moving in random directions with temperature. The overall direction is in the direction of the current. So, with temperature, as you increase temperature, all of these electrons, even though let us say there is no current, okay, let us say you have a static situation. If as soon as you have some material which is filled up with electrons, all of these electrons are really jumping around based on how much energy they have. This is statistical thermodynamics. They have energy because the temperature is high or whatever, there is a non-zero temperature. So, they all have energy. So, they all are really moving around in 3 dimensions, right. You can do your statistical thermodynamics and figure out all the 3 dimensions, etc., what are the different energies in all these 3 dimensions. So, all these electrons are moving around. Now, as the electrons are moving around, what is really going to happen is a potential is going to be developed across this particular element. This element is a piece of resistor. Okay. As electrons are moving around over the resistor, they are going to develop a potential. So, it can be shown that if this resistor has a resistance of R, if this resistance is 0, then as the electrons are moving around, even though they have a lot of energy in them, they can move around, the resistance is 0, the potential developed across the resistor is 0. So, it is really not of much consequence. However, if the resistance is non-zero, you have got some resistance over there, they are going to develop a potential across that particular element. Okay. So, it can be shown that the potential that they develop is 4 kT times R times delta F. This is the power spectral density. I am sorry. This is the power spectral density of the voltage that is developed across the resistor. All right. It is not very clear, right. Okay. Once again, the electrons are jumping around. Okay. The voltage that they will develop, the mean squared voltage over a little bit of bandwidth in frequency is so much. It is proportional to temperature, it is proportional to the resistance which we do expect, and it is proportional to the Boltzmann constant, and you can work this out using statistical thermodynamics. There is a 1929 or earlier, I think it is 1929 paper written by a gentleman named Nyquist. Proving this result. You have heard of Nyquist, right? Okay. You are all electrical engineers, you should hear about Nyquist, Nyquist sampling rate, Nyquist theorem, Nyquist method of stability, etc., etc., Nyquist plots. All right. So, this gentleman figured out, has proved in a 1929 or so paper, I am not sure of this, it is as early as that, that the mean squared noise voltage that you are going to see across this resistor over a given band of frequencies is 4 kTr times df, where df is the band of frequencies. Okay. So, a resistor is really going to be modeled by a resistor in series with a voltage source, noise voltage source, okay. So, this is going to be the model of the resistor. Across the resistor you can see that you are going to get a certain noise voltage. Now, this noise voltage does not have a sign, it can't possibly have a sign. You can't possibly have only positive noise voltage or only negative voltage. Mean noise voltage should be 0, mean squared noise voltage is so much. So, we usually do not put this plus and minus symbol over here, we sometimes like to put a star. A lot of people have lot of different conventions as to how they denote this as a noise voltage source. A lot of people just put a circle over there, put nothing inside, and to show that it is a noise voltage. All right, then you write that it is a noise voltage source. Okay. Now, if this resistance is 0, if this resistance happens to be 0, do you think there is going to be any noise voltage? No. So, suppose I have got an inductor, an ideal inductor which does not have any resistance. The noise voltage developed across the inductor is going to be equal to 0. Okay. Similarly, if I have got a capacitor, the noise voltage developed across the capacitor is going to be equal to 0. Now, you can show from this that wherever you have got lossy elements are elements that consume power, that convert electrical energy to heat energy, those are lossy elements. Lossy elements will create noise, elements that do not have any loss in them will be noiseless. This is just an extension of this, right. If you have got a diode, for example, okay, if electrons jiggle around inside the diode, then they will develop a potential. If you have got a MOSFET, channel of the MOSFET, electrons are jiggling around the channel, or let us say electrons are jiggling on the gate. Okay. Then they develop a potential across the gate source. once they develop a potential across the gate source, it creates a noise, right, noise in the current. So, all of these are noisy elements. Inductors and capacitors are noiseless elements. Inductors and capacitors are also lossless elements, all the others are lossy elements. You can also put mutual inductances in this group. Of lossless, noiseless elements. So, if you make a circuit which is passive and lossless, then it is also going to be noiseless. It is not going to add any noise of its own. All right. Next thing to observe is that as you decrease temperature, the noise is going to decrease, right. At 0 Kelvin, the resistor is noiseless, but at 0 Kelvin no electrons move at all in fact. So, things are very different at 0 Kelvin. So, we can't really talk about that temperature. Next observation, we have got the resistor modeled as a resistor in series with a noise voltage source. Okay. Let us say Vn is the noise voltage at any given point of time. This can be modeled as a resistor in shunt with a noise current source. Thevenin to Norton conversion. Okay. And if the mean squared noise voltage is Vn squared, then the mean squared noise current is going to be Vn squared by R squared. Okay. If the mean squared noise voltage is 4 kTr dF, right. So, this is the alternate model for a resistor. You can have a noise current that is going, it is really modeling the electrons moving around. Once again, if there is no resistance over there, if the resistance is 0, then even when the electrons are moving around, it does not matter because it is a short circuit. So, all of this current is going to go through this loop. So, it does not matter, even if the current is very large, it does not really matter. All right. So, this is what we have got so far. These are the different noise mod. This is the model for a resistor. Next step is what happens when you put two resistors in series. You should see, you should be able to replace two resistors R in series with one resistor which is really 2R. All right. Now, two resistors R in series can be modeled when they are noisy. They are going to be modeled as two noise voltages in series with 2R. But what you have got to remember is that these voltages are mean squared noise voltages. Okay. Then what you have got to remember is that these are noise is a random process. When two mean squared noise voltages come in series with each other, it is not the same as series voltages. Okay. What? So, let us say this is Vn1, this is Vn2, then really what is the voltage? The voltage I have is Vn1 plus Vn2. Okay. So, the mean square noise voltage is going to be this. Right. Now, noise voltage number 1 is 4 kT RDF, noise voltage Vn2 squared is also 4 kT RDF, but Vn1, Vn2 mean of that is going to be equal to 0, because these are two random processes which are uncorrelated with each other. So, when you do the mean of the product, it is really going to be equal to 0. So, this third term will not be present, and so what you are going to get is that the total noise is going to be Vn1 squared plus Vn2 squared, which is exactly the result that you want. All right. We are going to carry on from this point in the next class. So, we are discussing noise, and we are discussing ways to work around with noise, work with noise and model noise, etc. So, so far we have talked about the resistor, which contributes 4 kT RDF as the mean squared noise voltage, and we have also discussed that only lossy elements contribute in terms of noise, everything else is noiseless, inductors, capacitors, mutual inductances. Okay. So, let us stop here and we will proceed from here in our next lecture. Thank you.